Hello children, welcome to VKS's physics clinic, and this class is going to be very unique because we will be discussing waves. In fact, waves are a very interesting chapter. We have many interesting concepts in it that we can bring across. It says that what is the wave? Wave. What is a wave? Wave basically is a disturbance. A series of disturbances which are produced by a periodic force. So wave is basically what? It's a form of energy or a disturbance which is produced by an external periodic force. Very important. Now, in a wave basically we have transmission of energy through a medium. May not be a medium, but most of the cases it has to be a medium. Transmission of energy, in fact, is what you are calling a disturbance, and the disturbance is being produced by what? A periodic force. So let's define what is a wave. First, we will define what is a wave. Wave is force. So this disturbance which we are talking about, in fact, will be transmitted through a medium only by the vibration of the medium particles. For understanding wave, we can understand a very simple experiment. Imagine the game of pinball in which a number of pins like this arranged. There is another pin out here, and all these pins have been arranged on the table, right? And they are placed very close to each other. What you find that if you push one of the pins, then this pin will push this, and automatically you will see the disturbance will continue to travel. One push, and then what do you find? The disturbance starts traveling from one end to the other. I am not disturbing the other side, I disturb just one, and all will start what? Moving in the same direction. This is basically the wave which you talk about, the transmission of the disturbance through medium. Now, it's very important to understand that wave we are talking about is basically a form of energy. Right? And energy has to be transmitted through a medium. So, if it's a mechanical wave, for example, then we need mass for storing and transporting this energy. Clear? So, children, once understand the concept of waves, let's see another example. Suppose I join a number of springs. One spring is here, one spring is here, one spring is here, and this spring is here. I just pull one string and one spring and release. Then what we find? That this vibration is transmitted to all the springs one by one, and the entire set starts what? Is set into motion. Right? This is another term that we talk about is pulse. Pulse is a small part of this disturbance. Pulse is a small part of this disturbance. For example, you take a string, tie a descent, and give it a small vertical jerk at one end. So you will find at one instant, here we have a pulse. Small part of the disturbance is called what? Pulse. So this can be considered as what? Pulse. This small part can be considered as what? Pulse. A small part of the wave that is traveling and the disturbance which is traveling is actually considered what? A wave. Now we can have yet another part like this. This is another pulse. You can have yet another part. This is another pulse. You can have yet another part which is another pulse. And this is how the wave gets what? Propagated through a medium. Clear? But every time I talk about a medium. But don't be under the impression that a wave will always require a medium. For example, electromagnetic waves do not require medium. Light which is traveling from sun and reaching earth is mostly traveling through light where there is no what? Medium. Right? So when I'm talking about medium, I'm talking about mechanical waves. So we can briefly see what is the classification of waves. How many types of waves do we have? Classification of waves. So remember children, waves will be propagated if and only the medium particles are vibrating. They are moving. Okay? Classification of waves. we have mechanical waves, then we have electromagnetic waves, and then we have matter waves. So what are mechanical waves? Children, mechanical waves are the waves which require medium for their transmission. Require medium. Now, mechanical wave requires medium for the propagation. Because suppose you are the finest guitar player and you try to play guitar in a region which is a vacuum, so nobody will be able to hear it. If two friends want to talk to each other in vacuum, they will not be able to hear each other because there is simply no medium to carry their waves produced by them, right? So we need a matter particle to store and transmit the energy. Now, electromagnetic waves. So these waves are mechanical waves are produced by what? Vibration of medium particles. Vibration of medium particles. If medium particles are not vibrating, these waves do not propagate. Mechanical waves. Now, what are electromagnetic waves? They do not require medium for their propagation. They do not require medium for propagation. Electromagnetic waves do not require medium for the propagation, as you know already. They travel at the speed of light. Clear? Now these waves are not produced by vibration of any particles, but they are produced by oscillating electric and magnetic fields. Right? When I have an electric field here, okay, and then a magnetic field, and these two fields are oscillating at right angle to each other, then the wave which is produced is called electromagnetic waves. We will be having a full discussion on this in class 12, right? I can consult my videos on electromagnetic waves in class 12, you will be able to know from there. So, mechanical waves are produced by vibration of medium particles. Electromagnetic waves, they do not require medium for their propagation, and they are produced by vibration of electric and magnetic fields, right? This much you know for the time being. Now, what are matter waves? In fact, you must have read in chemistry de Broglie's theory of matter waves, a dual nature of matter and radiations. So, matter waves are the waves which are associated with microscopic particles, okay, subatomic particles. So, waves associated with matter actually called matter waves. And these are, these waves so far have been detected only for microscopic particles, large objects. Their matter waves are so far we have not been able to detect. Difficult to detect because wave becomes very small. So, matter waves are waves associated with microscopic particles. So, children, in this chapter we are going to basically deal with mechanical waves which require medium for their propagation. So, we understand one very important thing from this discussion, that mechanical waves in fact actually produce when particles are vibrating each other. So, what is the mode of transmission of this energy? Okay. So, let's check what is the mode of transmission of mechanical waves. What is the mode of transmission? Now, children, characteristic of propagation of mechanical waves. How mechanical waves are? In fact, it's very important for you to know two things. Number one, the mechanical waves are propagated by the vibration of medium particles. Now, the second thing is, during propagation of mechanical wave through a medium, net displacement of medium particles is how much? Zero. Very interesting. 2 points. First one is during propagation of mechanical waves. The first one, during propagation of mechanical waves During propagation of mechanical waves, medium particles oscillate about their mean position. Suppose I choose a particle out here, it will oscillate. It will oscillate when you go to the right, come to the left, and again pass to the mean position. This is what it means. So this motion you can understand is like a periodic what? Oscillatory motion, right? Something like what? Simple harmonic motion. Now the second most interesting thing is that net displacement. Now this is second point which is very important. Net displacement of medium particles is zero. Yeah. Means the simple harmonic oscillations are fine. But you have to understand this, that the particle starts from here, moves to the right to the extreme what? Distance, and then passing this energy, like particle A passing energy to particle what? B, and then again B moves, transfers its energy to what? C and comes back. A transfers its energy to B and comes back. B transfers to C and comes back. Similarly, C will transfer its energy to D and come back. And again, take energy at the periodic source and again move, and the energy keeps what? Traveling from one end to the other end. So you can see it's a series of transfers of energy, but the medium particles are not taking any displacement at all. They will, if I transfer the energy to this particle goes and transfers to the next particle and comes back. Now this particle goes, transfers to the next particle and comes back. This is how the energy is getting propagated through the medium. When I'm speaking, for example, when I'm speaking now, my voice is acting like what? A periodic force. And then every time I speak, I'm producing disturbance, and the medium particles are taking energy, they're going to the next particle, transferring the energy coming back. Now the particle here goes to the next particle, transfers energy and comes back, and this sequence goes on till when? Till the damping will kill all the energy. Right? Till the damping will kill all the energy. If I'm speaking in medium, but there is no damping, then if I hear from one end of the world, it will be heard to the what? Other end of the world, if there is no damping of what? Oscillations. So you can understand the mechanical waves will be produced by vibration of medium particles, and net displacement of the medium particles will be zero. They can vibrate sideways, or they can vibrate what? Up and down. They can vibrate either way, but there will be no displacement of the particle. They will move, come back again, move, come back again. Come here, take energy, again come, go on the other side, transfer the energy and come back. But there will be no displacement of medium particles. Now for transmission of mechanical waves, the medium should have certain characteristics. Okay? So what characteristics are required in the medium? Medium characteristics. Medium characteristics, you understand? Means what should the properties of the medium so that it is able to transfer what? Energy as what? Wave. First one is it should have elasticity, but not necessarily elasticity always. Elasticity is required only for transverse waves, okay, or volume strain, which is required for longitudinal wave. So you should be having elasticity. You should have elasticity or volume strain. First condition. Second condition. You should have mass, or inertia. Because if it is not having mass, it will not be able to store energy, and the particle is not able to store energy. However, even if I give it energy to reject it, not able to store that energy, and if it is not able to store energy, it will not go to the next particle. Like passing the buck, like a relay race, you run with the baton and then pass the baton to the next runner, and then he runs and passes to the next. This is what the wave motion is all about. The energy is coming from A to B, B to C, C to D, and the particle of transferring energy is coming back to its what? in position. For transferring energy, you should have what? Mass or inertia factor, which is very important, and less viscosity. Now, this less viscosity is desirable but not must. Less viscosity, I will be able to transfer energy over longer distance. More viscosity, I will not be able to transfer energy over longer distance. Clear? So, these are characteristics of the medium and the characteristic of propagation of the wave that we understood. Now, children, listen, how many types of mechanical waves we have? Types of mechanical waves. How many types of mechanical waves you have, children? We have two types of mechanical waves. One is called transverse wave, and the other one is longitudinal wave. How many types of mechanical waves you have, children? Two types. One is called longitudinal wave, the other is called transverse wave. So we will be studying what exactly are they and how do they differ. But when we discuss these two waves, you need to keep in mind that a wave will be produced only by the vibration of the medium particles. It is a mechanical wave, right? There is no vibration of the medium particles. They will not be able to produce any waves. Clear? So, what are these two waves we will be discussing now? Now, children, we will discuss what are transverse waves. Transverse waves. Let's answer transverse waves. You have seen musical instruments, for example, or a string for that matter. I have a rope, this is a string or rope, and then if you jerk it at free end, you would jerk, then what do you see? The wave travels like this. Something like this happens. Yes? Now what do you find? That the wave is actually traveling like this. This is how the wave is traveling. Let's make it like x-axis and y-axis. You can see the wave is traveling on x-axis, horizontal direction. But particles of the string, how they are oscillating? They are oscillating perpendicularly. Yes? If we consider a particle like this, it's moving up and down like this, goes up and comes down. A particle here goes up and comes down. Particle here goes up and comes down. This particle also goes up and. Similarly, if you take a musical instrument like guitar, sitar, all these instruments, and if you plug it at any point, then again you find a wave like this, like a sine wave. Right? Now, the pattern of this wave will depend upon when you plug the string. That's what the master is. The one who knows how to play guitar, he plugs the guitar at a certain point and produces different what? Frequencies. Now, what we understood about this transverse wave is, the wave is traveling horizontally, like this, but the particles are vibrating what? Up and down, which is perpendicular to the direction of propagation of the wave. Then this type of wave is called transverse waves. Meaning, those mechanical waves in which particles vibrate perpendicular to the direction of propagation of the wave are known as transverse waves. And you can see that the particles are slightly having two types of displacement. One is along positive direction, the other is along what? Negative direction. So, there are two lobes, one is positive and the other is negative. So, these lobes, they have a peak in the positive direction and a peak in the negative direction. These are called crests. These are called what? Crests. These are crests. And the negative maxima here, they are called troughs. Okay, so we have crests and we have troughs. Right? So what we have told children, let's go back to this again. Transverse waves are the waves in which the particles of the medium vibrate perpendicular to direction of the wave. Means if the wave is going like this, then the particles are vibrating like this. Clear? And this wave you can see is traveling in the form of what? Crest and troughs. What's a crest?
Positive.
Maximum displacement along the positive direction. What's a crest? Maximum displacement along the negative direction. So it's different water transverse waves. Those mechanical waves. So children, we define those mechanical waves in which particles of the medium vibrate perpendicular to the direction of motion or propagation of the wave are called what? Transverse waves, and this will be propagating in the form of crest and this is trough. Okay. So what is the characteristic of the medium? Means what kind of medium can produce actually transverse waves? You see, for producing transverse waves, the medium is equal to elastic in nature. It has to what? Elasticity. Because it should be able to handle shearing strain. Should be able to handle what? Shearing strain in the form of pressure. Yes? So, the criteria that the medium will be able to have transverse waves if and only if it is elastic. So, we know the metals are elastic, so metals can have what? Transverse waves. Then how about liquids? You know the liquids also have what? Surface tension. And as because of surface tension, they are elastic on the surface. So therefore, on the surface of the liquid also we produce what? Transverse waves. You have seen when we throw a stone on the surface of water, the water on the surface moves like this. But this doesn't happen inside. It happens only on the what? Surface. Why? Because the surface is got what? Elasticity is due to surface tension. Right? So what is the criteria? Criteria for transverse waves means what kind of medium can produce what? Transverse waves. Number one, medium should be elastic. Medium should be elastic. Why medium should be elastic? Because it involves shearing strain. Okay, that's why it should be elastic, and therefore it can be produced in. It can be produced in solids or liquid surface. But in the bulk of the liquid it cannot be produced because the bulk of the liquid has no surface tension. Surface tension is there only on the surface. And then the third part is same, should have inertia. Should have inertia. And the ideal situation should have low viscosity. In ideal case, it should have zero viscosity, but it is impossible to imagine the medium with zero viscosity. So, criteria for transverse wave is medium should be elastic. So, they can produce what? Metals or solids also on the liquid surface. So, you have what? Inertia and should have low viscosity. Clear? So, you will see what are transverse waves. Okay? Now, we have longitudinal waves, for example. Longitudinal waves. Longitudinal waves. Children, in case of transverse waves, the medium particles are vibrating in a direction perpendicular to the direction of propagation of the wave. Now, whereas we will be discussing what are longitudinal waves. Longitudinal waves. Now imagine a situation in which I take a a tuning fork and strike in a rubber pad. What do you see? The prongs of the tuning fork is set into motion. Now, as they vibrate, then what we do is they deliver pulse to the medium. Imagine a situation. This is prong A, this is prong B. Imagine a situation in which the prongs are moving to the right. When they move to the right, what do? They compress the air out here. What do? They compress what? Air. They compress air. So after vibrating to the right, they come to the what? Left. And it becomes something like this. This is the actual tuning fork. Now it will become something like this. It becomes something like this. The prongs are vibrating to the left. So what will you see? That the air on the left will be pushed. The air molecule particles will come closer. And then they will be compressed. So while the prongs are on the right, then the air on the left is what? Rarefied. Right? When the prongs are on the left, then the air on the right is what? Rarefied. So if you combine these two states, then you can state very clearly that when the tuning fork is vibrating, then it is going to produce changes in what? Volume. Means it's going to produce not steady strain, but it's going to, because there is no change in pressure as such, there is change in what? Volume. So it's going to produce what? Bulk strain. Right? With the volume of medium particles will what? Change. So how will it change? At some point they will be compressed. See here they are compressed, and alternately they will be rarefied. Again, I combine these two. Again, if I combine these two, again they will be compressed. See, these are compressions. I make it look dark. Again, these are compressions. Here we have particles. And again here will be rarefied. So you see, we find that the wave is turning like this, and the particles of the medium also vibrating in the direction of propagation of the wave. They are not vibrating like this, they are vibrating like this. Then this wave is called what? Longitudinal waves. Meaning those waves in which the particles of the medium vibrate in direction of propagation or motion of the wave is called what? Longitudinal wave. For example, sound waves, waves produced in outer pipes, they are what? Longitudinal waves. So defining those waves, longitudinal waves. For example, sound waves are what waves? Longitudinal waves. Now let's have in the form of compression and rarefaction. Very important. The points where particles are closely packed, the regions where volume is highly reduced, in fact, will be called compressions. When the particles are compressed, they are brought closer. The pulse will push them close to each other. So these are compressions, and we generally remember C. And the regions in which the particles are separated from each other is called rarefactions, and we denoting in what? So your compressions will be what? Rarefactions. Clear? So what you observe? In case of a transverse waves, the medium particles are vibrating. The wave is turning like this, the medium particles are vibrating perpendicular. Whereas in case of longitudinal wave, the medium particles are vibrating in the direction of the wave. Okay? So we will show the meaning of compression and rarefactions. Now, what is the criteria for a medium to propagate longitudinal waves. What is the criterion for the medium? A criteria, which is multiple criteria. Now the first thing is that in this case, elasticity is not required because it works on the fluctuation of volume stream, right? So elasticity is not required. If you have elasticity, is fine. If you don't have, then also it is fine, as equally fine, because we are not going to work on the shearing strain, right? So it can be no elasticity is required. We don't require elastic medium. If you have elasticity, it is fine. If you don't have, then also it can be produced. That means it can be produced in solids, liquids, and gases. In all kind of medium, it can be produced. All kind of matter can be produced in solids also, liquids also, and gases also. And then the third universal criteria is it should have inertia. It should have inertia. And the fourth criteria is low viscosity. Low viscosity is always desirable because low viscosity will ensure that the wave is able to propagate over long distance. Clear to me? Once you understood it, we were discussing the crucial part, which is equation of a mechanical wave, and we were discussing equation of sine wave, which is progressive. Remember this word progressive. We will be doing later on coming across. We will discuss about equation of waves. We have standing waves or stationary waves. We don't move at all. But right now we are talking about progressive wave, which when I am speaking from here, I can be heard over a long distance with the wave is traveling. So a traveling wave is called what wave? Progressive wave. So we see the equation of a progressive wave now. Now children, we will be discussing the equation of progressive wave. But before that, there are certain terms that we use it very often. Key terms. You are familiar with most of these terms. First one is frequency. We will denote it by F or mu or N. I can use any of these terms. We prefer to use what? Nu. Frequency. So you already know. Number of complete oscillations per second is called frequency. Right? So I don't know, define it already. And its unit is hertz. High units are like kilohertz and megahertz. So frequency, number of complete oscillations per second. Now many times in the matter of like RPM, revolutions per minute. So what will you do? Divide by 60 and convert it to per second. Okay, so that's frequency. Now number 2 is time period. Time period is the amount of time taken for one complete oscillation is called time period. For example, if I have a sine wave, then from here to here it is what? One complete time period. Clear? Or let's see, from here to here is also one complete time period. From here to here also it is one complete time. So time period is basically the interval of time between which the two particles either complete what? Incomplete phase or in the same state of motion. For example, here you can see the displacement of both particles is maximum. Displacement of these two particles is what? Maximum. It's not necessary it has to be crest and trough. I can take two particles. If this moves through a distance, suppose delta, and I consider another particle separated from this trough by a distance delta, then this gap will also be what? One time period. Clear? So time period is time taken to complete one full cycle is called time period. And there is definite relation between frequency and time period. Please remember that frequency equals to by time period. We write V is equal to 1 by T. These are important relation. Okay. And then we have angular frequency. Angular frequency, in fact, is another term angular velocity. We denote it by what? Omega. And omega you already know is 2 pi by T or 2 pi. Clear? Now we have another term called wavelength. We denote it by what? Wavelength. Now what is wavelength? Wavelength, children, can be defined as the distance traveled by a wave in one time period. A wave is traveling. So in one time period, how much distance is traveling is called what? Wavelength. Here we will be defining distance. So children, distance traveled by a wave in one time period is called wavelength. Suppose wave is traveling like this. This is how the wave is traveling. And one time period it goes from A to B. So this distance will be what? Now children, this wavelength can be very easily calculated for transverse waves or for longitudinal waves. Remember this trick number 1. Transverse waves wavelength is distance between any two consecutive drops or any two consecutive what? Crests. So transverse wave is what? Distance between transverse wave wavelength is the distance between any two consecutive crests or drops is called wavelength. Is called wavelength. So if we consider these two crests, then the distance is what? Wavelength. And if we consider these two troughs, then also the distance is what? We can consider another example. If we take a case of suppose longitudinal waves. Then for longitudinal waves, the distance between longitudinal waves, it is distance between two consecutive rarefactions or compressions. If we consider the case of a longitudinal waves, then the distance between any two consecutive compression or rarefaction is called what? Wavelength. For example, suppose I have this is a compression, this is compression, and this is rarefaction. Again I have compression. So this is, you can see, compression, and these are rarefactions. If I take midpoint of these compressions, let it down here, then this distance is what? Or if we consider this is midpoints of rarefactions here to here, then this distance is also clear. So what we have shown, the distance between any two consecutive crests or any two consecutive drops is equal to the wavelength, you would say transverse wave. Or distance between any two consecutive compressions or any two consecutive refractions is wavelength, you would say longitudinal wave. So you must be very clear about this. Now there is another term which we will talk about, number 5, and wave velocity. Wave velocity. You see children, whether it's a case of transverse wave or whether it's a longitudinal wave, in both the cases, each particle vibrates with one different velocity. Here you find that every particle is vibrating with one different velocity. But velocity of the wave remains what? Same. Meaning, velocity of wave is different from velocity of the medium particles. Okay? So, how we define a wave velocity? Wave velocity is basically the distance traveled by a wave in 1 second or unit time. Okay? So, to define displacement of a wave is called wave velocity. And wave velocity is equivalent to what? V. Now, there is a unique relation between wave velocity, wavelength, and frequency. You see, when you define wavelength, you know what it is? Distance traveled by a wave in one time unit is called what? Wavelength. So we know that velocity v is equal to what? Distance upon time. Right? So v is equal to, when the distance is left or wavelength, then time is how much? T. And 1 by t is equal to how much? Frequency. 1 by t is equal to mu. So v is equal to how much? Mu into. So we had a simple discussion on the relation between velocity, frequency, and wavelength. Now, in this video we will be covering only this much topic. Okay, thank you.